Hi, today in this video we are going to learn about the third law of thermodynamics and calculation of entropy using third law. Now, before before I tell you about the third law of thermodynamics or what is the statement of third law of thermodynamics, I would like to brief about what is entropy. So, we can understand entropy as the degree of randomness or degree of disorders. That is, if there is a system, then the number of positions the components of systems can take place randomly, that can be assumed as the randomness or disorderedness. Like if it is in a room, then we can put clothes everywhere, anywhere. So these are the number of randomnesses where uh, we can put the clothes. Then that is why the entropy is, if there is a unorganized way, then the entropy is higher. If the clothes are organized, then the entropy is lower. So the entropy is nothing but the degree of randomness, and it arises due to the different kinds of motions. These motions can be understood in three ways. That is, one is vibrational motion, other is rotational motion, and the last one is transitional motion. Now, the vibration motion again can be understood like this. If it is a molecule, then if a molecule is moving like this, suppose from this state to this, and then again this state to this is termed as bending. Similarly, if a molecule is like this and if it gets stretched like this, then this is called your systematic stretching or stretching. And again, if the molecule do not stretch equally from the both sides, then that is called asymmetric stretching. Now, moving ahead, similarly, the rotational motion can be understood that if these are the three, sorry, fortunately I am successfully drawn this. So if this is the molecule and if it is rotating like this, then this is a rotational motion. And similarly, if a molecule is like this and moving in this way only, then this is your transitional motion. So basically, till now we have understood that there can be three types of motions, and on the basis of that there could be entropy. Now if we come to a temperature that is 0 Kelvin, then this is our absolute temperature or absolute zero, at which the entropy is assumed to be zero. Now why this is so? Because at absolute zero, that is T is equal to 0 Kelvin, the system is assumed to have no motion classically. That is, we are not talking about quantum motions. Then, if we consider about an absolute zero, then there will be only one position for each and every component of that system to be present. Or if we understood it as a crystal, then at absolute zero there is only one possible location for each atom or molecule comprising that crystal. So in that case your ohm will be equal to 1, and according to Boltzmann's equation, entropy will be equal to k ln ohm. Ohm is equal to 1, so that is equal to k ln 1. Ln 1 is equal to 0, so s will be 0. That is, at absolute 0, which is an ideal temperature, it is unobtainable. A perfect crystal also is an ideal crystal, and combination of both two is leading to the third law of thermodynamics. Or we can understood it as that at absolute 0 the entropy is 0, and what our third law of thermodynamics says that at just a second, the third law of thermodynamics says that if the crystal is pure and perfect crystalline and temperature is 0 Kelvin, that is absolute 0, the entropy will be 0. So this is what is the statement of third law of thermodynamics. Now how this how this temperature helps us in, how this statement helps us in calculating the entropy change, that is delta S. Now for this we have a table, and the table can be here. So this is the table. Here we can see that the entropy at standard temperature is given for different substances, and on the basis of that we can calculate the entropy. How? Let's discuss here. So now, before moving to the calculation of change in entropy, I would like to show you a graph by drawing that how the entropy changes with the changing in the state. So if here it is entropy, here it is temperature. Now if we look closely, then this is your solid state. Then there is a, let me change some color so it is properly visible. Then again, this is your liquid. This is gas. So here this is actually the change in entropy due to fusion, and this is a change in entropy due to vaporization. As we can see that at this temperature boundary T1 there is a change in the state from solid to liquid, and there is a increase in the change, though there is a sharp increase in the change in entropy. And similarly here also there is a change in from liquid to gas, and this is change in entropy due to vaporization, and this is due to fusion. So we can see clearly that the S naught for gas is very greater than S naught for liquid, which is greater than S naught of solid. Now the what is here S naught is our standard entropy at pressure 1 bar and temperature 298 Kelvin, and it is sometimes also written as delta S naught at 298 Kelvin. So now let's come to how the delta S for a system can be calculated. So delta S for a system can be calculated as S naught at 290 Kelvin of the products. If there is a reaction going on and the we need to calculate the delta S naught or the change in entropy due to the reaction taking place, then we can calculate the change entropy change using the equation reactants. Here this is nothing but the coefficients of stoichiometric coefficients in a balanced chemical equation. So if we take an example of an equation, suppose reacts to form Ma plus Nb reacts to form Xc plus Yd, then delta S naught for this reaction will be given as X into delta S naught at 298 Kelvin for C plus Y into S naught at 298 Kelvin for T minus M into S naught at 298 Kelvin for A plus 298 Kelvin for B. So this is how we can calculate the entropy, and these values are known to us using some calorimetry. So using this we can calculate the change in entropy when a reaction takes place. Now let us take an example. Now take the example of, let's say we need to calculate the delta S. We need to calculate the delta, what's happening here? Let us calculate the So let us calculate the delta S naught for the reaction of liquid isooctane with O2 at 298 Kelvin. So this is a clearly combustion reaction in which liquid isooctane is C8H18, which is reacting with O2 to form CO2 plus H2O. This is a simple combustion reaction. Now we need to first balance the reaction. So let's balance that. It will be equal to 25 by 2, and then this is 8 CO2 because of this 8 carbons, and there will be 9 water molecules. So this is how the reaction is balanced. Now back to this expression. This we can write that delta S naught for the above reaction will be equal to 8 into S naught of CO2 plus 9 into S naught of H2O minus S naught of C8H18 plus 25 by 2 into S naught of oxygen O2. So this will be given by, this can be noted from this table. This is for O2, H2, sorry, H2O, this is O2, this is isooctane, and this the one remaining is carbon dioxide is here. So noting down these values, we can write it at 8 into S naught of 213.8 joules per mole per Kelvin in plus 9 into 188.8 joules per mole per Kelvin minus 1 into 329.3 joules per mole Kelvin plus 25 by 2 into 205.2 joules per mole per Kelvin. On calculating, we can get delta S naught will be equal to 515.3 joules per mole per Kelvin. So this is how we can calculate the change in entropy, and it is always expected that the change in entropy should be always positive, as there is one large hydrocarbon molecule. This one large molecule is breaking down into smaller and smaller molecules, so there are too many gaseous particles and hence entropy should be increased. So this is how we can determine the entropy change in any equation. However, for an exercise we can use this equation to determine, and let's determine the change in entropy for the reaction at 298 Kelvin. So we will write delta S naught will be equal to 2 into S naught of CO2 plus 4 into S naught of H2O minus 2 into S naught of CH3OH plus 3 into S naught of O2. So again, reading from the wet table, this is one extra, so noting down, we can write 2 into 213.8 plus 4 into 70 minus 8 plus 3 into 205.03. So this comes out to be minus 161.6 joules per mole per Kelvin. Here, the thing to be noted is that the entropy change is negative, and this can be taken as because this is also liquid and this is also liquid, as there is initially 2 moles of liquid and now there is 4 moles of liquid. So because of this, since there is decrease in the gaseous particles, so the entropy is decreasing. Hence it should be noted that in some reactions, or it is because this is a small system, but if take it as a large system, usually the entropy increases. So keep this in mind, and I hope this is understood to you how to calculate entropy change using third law of thermodynamics. Stay tuned for the coming videos, and if you have any doubts, you can just WhatsApp your doubts on the WhatsApp number showing on the screen. Please feel free to ask, or if you have any other doubts or any review regarding the video, please do comment below. Thank you for watching. Kailasha Foundation, happy to help.